Very good afternoon, everyone. Thank you for joining the 7 webinar series of MyPCS in 2021. As what we had in the previous 3 sessions, today we are privileged to have Professor Manabu Kano from University of Kyoto, Japan. And today is going to share his research and some of his collaborative projects with other institutions as well as industries. This presentation today will be entitled Inferential Sensing and Control in Process Industries. So without further ado, so let's learn from him. And Professor Kano, the time is yours. Thank you very much.
Thank you very much for kind introduction, Agas. Okay, good afternoon, everyone. Today, I'd like to talk about inferential sensing and control in process industries and beyond. All right, I'm Manabu Kano, working at Kyoto University in Japan. So before starting my presentation, I'd like to ask all of you to, if possible, scan this QR code. If you have a smartphone, please scan this QR code, or you can use link. I'm copying and pasting the URL in chat. Okay, so you can access the website through this link. And once we open the window, then please try to use this application named Comment Screen. I would like to check whether this works. So if you scan this QR code and open the website, then please input any text, any comment here. Test. Deny. Okay.
Yeah, it is working, Prof. Kano.
Yep.
Yep.
Hello. All right. So please don't hesitate to make a comment here by using comment screen, or you can interrupt anytime you want to ask any questions. All right. So let's start. So, you know, this is a map of Japan, and this is a very old map. Actually, this is the first accurate map of Japan, which was drawn by Mr. Tadataka Ino, who was a samurai in the Edo era. He was born in 1745, and he surveyed all over Japan on his foot from 1800 to 1816 after his retirement. And this map was completed in 1821 after his death in 1818. And surprisingly, there is little difference between this map and the current latest map based on the satellite technology. And do you know where the city of Kyoto is? The Kyoto is located in the middle of Japan, and Tokyo is here, and the Tokyo is actually means East Kyoto. So the Kyoto is actually the central city in Japan. And my university, the Kyoto University, was founded in 1897 as Kyoto Imperial University. And in 1947, it was renamed as Kyoto University. And we have currently in 2020 about 3,000 faculties and 20,000 students, including graduate and undergraduates. And in Kyoto University, Our research group interest covers process systems engineering, PSE, medical systems engineering, MSc, and also agricultural systems engineering, ASC. These research topics looks quite different. However, in fact, they are very similar to each other. So in our research group, we found a common problem in these areas, and we try to develop our common solving tools for solving the problems, social problems. All right. So now let me talk about data-centered process operation. Let's say we have a process here to produce our products, and this process is usually controlled or operated by using a control system, such as distributed control system, DCS. And through this system, we can have a huge amount of process data or operation data. And by using this data, we can perform process control, process optimization, batch sensing or soft sensing, and process monitoring, including fault detection and diagnosis, and so on. Okay. And in order to achieve these technologies, in order to use these technologies in practice, the key to success is model. If we have a good model, then we can do anything. If we do not have good model, then we cannot do anything, right? And in order to build models, we have two options. One is the use of first principles or physical laws and chemical laws. This type of model is called first principle model or physical model. The other direction is using data, process data, and applying statistical technique to process data, we can get statistical model. And this type of statistical model does not describe any actual relationship or phenomena in the process. So this type of model is called black box model. On the other hand, physical model or first principle models are called white box models. And of course, we have many models between black and white. They are called gray box models. Okay, usually gray box models consist of physical models and statistical models. Gray box model is a combination of them. Okay, now I would like to show you my favorite figure. This figure shows the relationship between chocolate consumption and the number of Nobel laureates. Okay, so this point here denotes the chocolate consumption, 10 kilogram per person per year. And this point, this vertical axis shows the number of Nobel laureates. Okay, please look at right top where Switzerland is located. Okay, so people in Switzerland ate a huge amount of chocolate, actually 12 kilograms per person per year, and they obtain a number of Nobel Prizes. On the other hand, look at Japan here, right? So we Japanese people do not eat chocolate much, only 2 kilograms per person per year, and we have a few Nobel Prizes. Okay, so I would like to increase the number of Nobel laureates in Japan. So my proposal is to distribute chocolate to any school, elementary school, junior high school, and so on. So I suppose in 10 or 20 years, the position of Japan moves from here to here, like US or UK. What do you think? Do you agree my proposal or not? Maybe not. But I found this graph in the paper entitled Chocolate Consumption, Cognitive Function, and Nobel Laureates. And this paper was published in the England Journal of Medicine, which is one of the top journals in medical area. And the author said that chocolate consumption enhances cognitive function, which is a sine qua non for winning the Nobel Prize. Wow. So I needed to say that we have to be careful not to be deceived by spurious correlation. Spurious correlation means that two or more variables are associated, but not causally related, in fact, due to either coincidence or the presence of a third unseen factor or factors. Okay, so correlation does not imply causation. In addition to spurious correlation, if we apply statistical technique to process data, we need to be careful about multicollinearity. Multicollinearity means that two or more explanatory variables in a multiple regression model are highly linearly correlated. Okay? As a result, the estimated regression coefficients may change erratically in response to small changes in the data, and the model becomes not robust. Okay, so if we use process data analysis, we need to be careful about spurious correlation and also multicollinearity, at least. Okay, today I'm going to talk about data analysis, in particular process data analysis. So I'd like to check your literacy of probabilities or statistics. So I have a quiz here. Please answer this question by using comment screen application. Okay, so here, you know a family has two kids, okay? But you do not know the sexes of them. Please answer the probability that both kids, two kids, are girls. When you asked the mother, do you have any daughters? And the answer is, yes, I have. In this situation, the probability that both kids are girls is 1/2, 1/3, or 1/4. Okay, please answer this question. Or 1/2. Okay. Any other answers? Oh, again, 1/2. Oh, 1/2 is dominant. Okay. Okay, okay. Oh, 1/4. Okay, good. Okay. Oh, but no 1/3, 1/2 or 1/4. All right. Oh, now we are using the application named Comment Screen. If you want to use this, please check the chat. I copy and paste the link to Comment Screen. Okay. Before answering this question, I have another quiz. Okay, the situation is almost the same. You know a family has two kids, but you do not know the sexes of them. And please answer the probability that both kids are girls when you ask the mother, is your elder kid girl? And the answer is yes, she is. She's girl. In this situation, please answer the probability that both kids are girls. Two kids are girls. 1/2, 1/3, or 1/4? Okay, 1/2, 1/2, 1/2, okay. Oh, 1/4. 1/4 is coming. All right. Okay, now I would like to explain how to solve this quiz. We have 4 patterns as shown in this figure: boy, 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 girl, girl, boy, and girl, girl. Okay, we have 4 patterns. And in the first quiz, we asked, do you have any daughters? And the answer is yes. So we can eliminate this boy, boy pattern from our list. And then the probability is 1/3 because we have 3 patterns and the correct answer is only this, the last one, right? So the probability is 1/3. And the second quiz, the question is your elder kid girl? And the answer is yes. In this situation, elder kid must be girl. So we need to consider these 2 patterns, and the correct answer is only 1. So the probability is 1/2, right? It's quite easy, I guess. Do you understand? So let's move on to another quiz. Okay, this is the last one. The situation is almost the same. Okay, you know a family has 2 kids again, but you do not know the sexes of them. Please answer the probability that both kids are girls when you saw the mother was walking with her daughter. In this situation, what is the probability that both kids are girls? 1/2, 1/3, or let me restart. So, first part of my presentation is about virtual sensing technology. Okay. So, okay, thanks. So, virtual sensing technology is a kind of technique that tries to estimate product quality that is difficult to measure online as a function of process operating conditions, which are easier to measure online, right? And we conducted a questionnaire survey in 2009 in Japan, and we asked process engineers which methods were used for developing soft sensors or statistical models, not statistical models, or models, okay? And the answer is shown here. The dominant approach is multiple linear regression or partial least squares regression. Both are techniques for developing linear models, linear statistical models, okay? And then first principle models, just-in-time models, gray box models, other linear models, and artificial neural networks. And it is surprising that the number of applications of artificial neural network is very small, only 3. I think in the last few years, this number of applications of neural network is increasing. But this result is convincing or makes sense because in the plant, we have to manufacture a product, and such product can be manufactured in a very small operating conditions, very small operation range. In such a small range, linear approximation is enough for building a model. So far, multiple linear regression and partial least squares are successful, have been very successful in practice. And in this questionnaire, we also asked the problem of soft sensors. And many engineers, actually 30% of process engineers, answered that the problem is accuracy deterioration due to changes in process characteristics. And 7% of process engineers answered that the problem is inadequate accuracy due to changes in operating conditions. So if we try to realize soft sensors or battery sensing technologies, then we have to cope with accuracy deterioration due to changes in process characteristics or operating conditions. And we don't adopt fixed model approach because the most serious practical problem is how to keep the high estimation performance or model maintenance. And model reconstruction is very difficult in practice. So in the last few decades, recursive approach was dominant. However, this approach might adapt a model to a new condition accessibly. And this approach cannot cope with abrupt changes in operating conditions or process characteristics. So my favorite approach is just-in-time approach. This approach builds a local model from neighbor samples stored in the database on demand or in a just-in-time manner. Just-in-time modeling is also called lazy learning or model on demand. These approaches can cope with changes in process characteristics as well as nonlinearity. And this approach builds a local model from past data around a query, which is a new sample, only when an estimation is required. Okay? And general procedure is shown here. First, when new input and output data become available, they are stored into a database. And then, only when estimation is required, a local model is constructed from samples located in the neighborhood around the query, and output variables are estimated. Then, after that, the constructed model, local model, is discarded after its use for estimation. And we repeat this procedure step by step. And when we use PLS, partial least squares, as a local model, the just-in-time modeling is called locally weighted PLS, right? And in this locally weighted PLS, we weigh all samples in the database according to the distance between the query sample and other samples. And by focusing on the samples close to the query, we build a local PLS model and estimate the output, for example, the product quality. Now, I'd like to show you several industrial applications of locally weighted PLS. The first one is from Sony Semiconductor Company. The target product is CMOS image sensor. Okay, and semiconductors, including image sensors, are manufactured through more than 300 process steps. And the final product quality is assured through electrical test, e-test, at the end of the process. Here, we focused on the dry etching process, and we would like to develop virtual metrology that can predict the etching conversion differential from process signals with high accuracy, even when characteristics of the dry etching tool change significantly. Okay? The problem is performance degradation. In fact, the prediction accuracy of virtual metrology or soft sensor decreases due to equipment maintenance events, including parts replacement and chamber cleaning. So we have to cope with that. Okay. So in this process, dry etching process, wafers, the intermediate products, are processed in 16 recipe steps, and 400 kinds of process signals are measured, and they are converted into 9 kinds of statistics, such as mean, range, standard deviation, and so on. So a total of 57,600 representative variables are used as inputs of statistical model. Okay, and this is a prediction results. Black line shows actual values, the measurement of etching conversion differential. And red line shows the prediction results of LWPLS. And blue line shows the prediction results of using SUM, which denotes sequential update model. Okay, and as you can see that locally weighted PLS is much better than the sequential update model, which is a kind of recursive technique. Okay, and the next example is from petrochemical industry, Showa Denko Company in Japan. We apply locally weighted PLS and model predictive control MPC to this process, consisting of 2 towers. In this process, we need to control impurity content in the product here. Okay, but it is very easy to decrease the impurity content by increasing the steam consumption. However, increasing steam consumption also increases the operation cost. So our real target here is to minimize operation cost by maximizing impurities content below its upper limit by using MPC. And what is the problem? The problem is that the impurity content in the product is only measured once a day. So operators becomes very conservative because the information about impurity content is not available. So we apply locally weighted PLS to predict the impurity content online or real time. Left-hand side figure shows the control results before implementing our inferential control system. You can see that the real impurity content, the black circles, are very low from this upper limit. So there is a big gap between the real measurement and upper limit because operators are very conservative to control this process. However, after implementing our inferential control system, the impurity content can be estimated real time, and we can move impurity content close to the upper limit. As a result, we can successfully reduce the steam consumption. In fact, the steam consumption was, in average, reduced by 25%. This was a very successful result for us. Now, I'd like to show you another example from pharmaceutical company, Daiichi Sankyo company in Japan. Okay, in the pharmaceutical industry, the concept of quality by design, QBD, is becoming very important. This is a concept in which quality should be built into a product with thorough understanding of the product and process. And to realize quality by design concept, PAT, process analytical technology, is becoming important. The PAT is a mechanism to design, analyze, and control pharmaceutical manufacturing processes. And PAT has been usually used for estimating or predicting intermediate product characteristics. Okay. So one example is shown here. So here we would like to estimate API content. API means active pharmaceutical ingredient in the blending process. Usually, API content can be measured or analyzed by using HPLC, liquid chromatograph, but it is time-consuming and expensive. So we'd like to use near-infrared spectroscopy, NIR, instead, and to build a model, calibration model, to estimate API content from spectrum of NIR. Usually, PLS is used in the world. However, here, we proposed to use locally weighted PLS instead of conventional PLS, because by using locally weighted PLS, we can achieve very highly accurate prediction. Okay? But we can further improve the prediction accuracy by appropriately define the distance or the similarity. Usually, similarity is defined by using this exponential function. Here, d is a distance. If the distance between the query sample and another sample is 0, then the similarity is 1. On the other hand, if the distance is very large, then the similarity, omega, is becoming close to 0, right? And the distance is usually defined as this conventional Euclidean distance, sometimes with weight theta. And by defining appropriately this weighting matrix theta, we can improve the prediction performance of locally weighted PLS or other types of just-in-time modeling. Here is an example. Here, we tried to realize rapid measurement of residual drug substances and excipients after cleaning process by using locally weighted PLS and IRS. Okay, so now let's think about, we would like to estimate the amount of magnesium stearate. Okay, and the problem is which wave numbers are important. So which wave numbers we have to focus on? If all variables are equally important, then we do not have to use this weighting matrix theta. However, if some variables are important, more important than others, then we have to use this weighting matrix theta, right? And in this case, which input variables are important, or which wave numbers are important? The wave numbers related to peaks here and here. So wave numbers corresponding to these peaks are important wave numbers or important input variables. So we proposed to use this spectrum of pure magnesium stearate as a weighting matrix directly. And this is a prediction result. Please look at the RMSEP root mean square error prediction. Okay, this is the error. And by using conventional PLS, RMSEP value is 0.354. If we use locally weighted PLS, RMSP became 0.319. So we can reduce the error by about 10%. That's good. However, if we apply locally weighted PLS with appropriate weighting matrix, then we can reduce RMSEP to just 0.215, which was drastically smaller than the others. Okay, So this kind of technique is quite important for improving the product quality, the prediction performance. Okay, now let's move on to the second part of my presentation, physical model and gray box model. Let me show you one industrial case study from Nippon Steel Company. Our target process is this continuous casting process. And in this process, controlling molten steel temperature in tan dish is quite important. Okay, if tan dish temperature is too high, it may cause breakouts. And if tan dish temperature is too low, it may cause clogging in the nozzle. So the tan dish temperature must be kept within a target range. However, the problem is that this tan dish, which is a large equipment, this tan dish has no equipment for changing or controlling the temperature. So in order to keep tan dish temperature at a desired value, we need to adjust the temperature just after the operation of RH process. So we need to develop a model that can predict and control tan dish temperature based on RH temperature and other process variables. Once we get this prediction model, then by solving the inverse problem, we can realize feed-forward control of tan dish temperature. And in the steel industry, usually practitioners and also process engineers love physical models. So we tried to develop a physical model of this process. First, we developed heat conduction model of the molten steel in the ladle. Our ladle is equipment here, which is used for transportation of molten steel. Okay, so this is a heat conduction model of the molten steel in the ladle. And of course, we need to describe the temperature distribution inside the ladle. And also we developed heat conduction model of slag in the ladle. And we need to describe the degradation of ladle due to very high temperature of molten steel. And also we need to develop a model of tan dish itself. And tan dish is very large equipment, so we cannot assume that temperature inside tan dish is constant or the same. So we applied compartment model approach. And we developed heat conducting model of the compartments. And finally, this is the prediction results. This graph shows the correlation between measured temperature and predicted temperatures. And RMSC value is 2.73, and the correlation between measurement and prediction is 0.74. But unfortunately, the prediction performance is not sufficient for industrial application. So we tested machine learning approach. In fact, we applied random forest to this problem. And this is a result. Just pushing button, generating random forest model, we got this result. RMSE if random forest is 2.08, which was much smaller than the error of first principle model. So our effort of making first principle model is useless? No, my answer is no, definitely no. Because we can upgrade first principle model to gray box model. Here is the answer. We have several approaches to develop gray box model. One is parallel gray box model. in this model, first we developed a first principle model and predict the output y, okay? Of course, we have prediction error, y minus yfp. And then we develop an outer statistical model which can predict prediction error of the first principle model by using process variables x. And combining the output of first principle model and this outer statistical model, we can improve the prediction performance. This is the first approach. And the second approach is called Sitter gray box modeling. In this approach, we estimate the best value of the process parameters theta by using an inner statistical model. And this inner statistical model estimates the best parameter values according to the process operating condition X. Of course, this serial gray box model and parallel gray box model can be combined into one, that is, combined gray box model. And we applied these three gray box models to that problem. And this is a prediction result. By using combined gray box model, the RMSE was reduced to 1.73, which was much smaller than the error of random forest or first principle model. So this approach was very successful. Okay. And here is another example of using first principle model. We developed an operation support system for blast furnace at JFE Steel Company. Okay, so target process is a blast furnace, which is a huge equipment. Actually, the height of blast furnace is 40 to 60 meters. And feed are coke and iron ore. Coke and iron ore are fed into this blast furnace from the top. And we produce the hot metal from the bottom, okay? Usually 10,000 tons per day. And inside this blast furnace, the temperature is almost 1500 degrees of Celsius. So it's very high. And in this blast furnace, there are very complex reactions. And there are solid, liquid, and gas phases. And usually it takes about 8 hours from the top to the bottom. And this process is so complex that operators are operating this blast furnace manually without automatic control. So our objective here is to develop an automatic control system, or at least operation support system, to realize more efficient and stable operation of the blast furnace. Okay. In order to realize such an operation guidance system, we developed two-dimensional transient model of the blast furnace by using the finite volume method with adaptive cells. Okay, so in this model, we automatically adapt cells according to the operating conditions to realize optimal balance between accuracy and the computational speed. And this figure shows the real operational guidance. Okay, in this situation, at the current time 0, the operation guidance system suggests to reduce delta PCR by -3. Okay, and this graph shows the predicted values of hot metal temperature without action, blue line, and with action, the red dashed line. By following this guidance, delta PCR equal -3 kilogram per ton, then we can decrease the predicted temperature, predicted hot metal temperature, right? And in order to realize this operational guidance system, we used nonlinear dynamic physical model and moving horizon estimation, MHE, and nonlinear model predictive control, NMPC. Okay, so these figures show the trends of blast moisture, which is a manipulated variable, and hot metal temperature, which is a controlled variable. Okay, the left-hand side figure shows the control results when operators followed the guidance. And right-hand side figure shows the control result when operators did not follow the guidance. And operators should have followed the guidance. Okay, so through these experiences, operators understand the usefulness of this guidance system. And now this guidance system has been used in many, actually in 4 steel plants for several years, and we have achieved the significant reduction of CO2 emission and the production cost. So this was a really nice, successful applications in the steel industry. Okay, please let me summarize my talk so far. It is important. Data utilization is very important. However, data utilization does not necessarily mean statistical modeling or machine learning. Domain knowledge is very important. We need to combine domain knowledge and data analysis to solve our problems. So this is one message from myself. Okay, now let's move on to the last part of my presentation, medical system engineering. So at the beginning of my presentation, I showed you this slide, right? So we have a plant to produce products. And this plant is operated by using a control system. And from this control system, we can obtain a huge amount of operation data or process data. And such data can be used for process control, process optimization, battery sensing, process monitoring, fault detection and diagnosis, and so on, right? However, these technologies can be applied not only plants, but also humans, because we want to know our current status, the current status of my body, healthy or not, okay? And if my body is not good, then we would like to know why my body condition is not good and what to do. To solve such problems, to answer such questions, we can use these technologies established in PSE area, process systems engineering area, right? Let me show you one example. That is epileptic seizure prediction. Unfortunately, in Japan, we had very severe traffic accidents. For example, in April 2011, 6 school children were killed by this crane truck. And just 1 year later, in April 2012 in Kyoto, the location is very close to our university, our campus. In this traffic accident, 7 people were killed. The problem is both drivers had been epileptic and they were advised not to drive, but they drove. So my question here is, should we take away their driver's license from the epileptic patients? I suppose the answer is no. So some people really need to drive a car. Okay, so I want to eliminate such accidents, traffic accidents, by our technology. So what is epilepsy? Epilepsy is a common and diverse set of chronic neurological disorders characterized by seizures. And 1% of population have epilepsy. So there are over 50 million sufferers, patients in the world today. But 70 to 80% of patients could lead normal lives if properly treated. But unfortunately, 20 to 30% of patients are intractable epilepsy. So we focus on such patients. Okay, let me show you some videos of actual epileptic seizures. So these are typical heavy epileptic seizures. Patients cannot move by their intent. Okay, so if such seizures occurs, they can live normally. Their quality of life is quite low, right? So our goal is to develop a seizure prediction system that can predict the seizure before it happens. And the system can improve the epileptic patient's quality of life by helping them to predict and prevent accidents such as falls, burns while cooking, and traffic accidents. Okay. The epilepsy is a disorder of brains. So in order to diagnose epilepsy, medical doctors are using EEG or brain waves. However, EEG cannot be used in daily life. I suppose you don't want to use this type of EEG cap in your daily life. So we need to develop another device. So we propose to use ECG sensor or heart rate variability. Heart rate variability, HRV, means the fluctuation of RR interval. RR interval means the interval between two R waves. Okay? And this RR interval, RRI, fluctuates like this. And this pattern, this fluctuation pattern of RRI represents the autonomic nervous function, and it is called HRV, heart rate variability. And this heart rate variability is quantified by using several indices, including time domain indices and frequency domain indices. And by using these indices or statistics, we can evaluate the current status or activities of autonomic nervous function. And maybe we can predict the seizures. Okay. So seizure prediction is a kind of fault detection or fault prediction. So we proposed to use MSPC, multivariate statistical process control. MSPC is very well known fault detection technique in the process industry and also in the field of process systems engineering. Traditional MSPC is based on PCA, principal component analysis, and PCA can capture the relationship among variables, process variables. So by applying PCA to time domain and frequency domain indices of HRV, we can capture the relationship between these indices. And we can define the normal region like this. And if the measurement is outside the normal region, then we can judge some fault happens. This is a basic concept of multivariate statistical process control, MSPC. And this is a result of applying MSPC to our patient's data. Okay, please focus on the right-hand side figure. I show T-square and Q statistics. And at this moment, the red vertical line, the seizure occurs. Okay, and before this seizure onset, a few minutes before, we can detect the fault, or we can predict the seizures by using MSPC. Okay, so this was great result for us. And now we are applying our system to real patients in several hospitals to test the performance in real situation. And our goal is like this. Okay, so patients wear our wearable ECG sensors, and we measure heart rate variability, or RRI. And the data of RRI are transferred to smartphone by using Bluetooth BLE. And in this smartphone, we analyze RRI data and apply MSPC or other fault detection technique to HRV indexes. And if we find fault, then we alert the patients. So this is our feedback system. And in the future, our seizure prediction system will be combined with fast-acting anti-epileptic drugs to eliminate seizures. So we want to eliminate accidents in addition to eliminate seizures. Okay. Thank you very much. Okay, now let me conclude my talk. Today, I talked about virtual sensing technology or inferential sensing technology and inferential control, which can be realized by using statistical model and also gray box model or first principle model. And I'd like to emphasize again that data utilization does not necessarily mean statistical modeling or machine learning. Domain knowledge is really important. If you are chemical engineers, the knowledge about chemical engineering is very, very important. And combining domain knowledge and data analysis, then we can solve the real problem. And also, just-in-time modeling is very useful for realizing virtual sensing technology or soft sensors. And just-in-time modeling, in particular locally weighted PRS, has been applied to many fields in chemical, refinery, and also steel, semiconductor, and so on. And from the viewpoint of systems engineering or systems science, PSC tools can solve medical healthcare problems and other problems in other fields. Okay, so if you are familiar with PSC and PSC tools, you can solve many problems, many different problems in many fields. You can do that, okay? And I'd like you to try. That is the end of my talk. Thank you very much for kind attention. I'd like to answer your question if you might have. Thank you.
Thank you, Professor Kano, for your insightful talk. I think we have seen your research group exploration to the applications of process system engineering, not only in chemical process industries, but you go beyond into some other application, including medical applications. So yeah, it's very inspiring, and I think we can see the potential, what potential of the process system engineering in many areas. So once again, thank you very much. So we open for open discussions. Any questions, any inquiry, any opinion from everyone? Feel free to unmute yourself. Otherwise, you can drop your inquiry or comment in the chat box.
Hello, Agus.
Yes.
Yes,
Yes.
Hendra.
Can
Yeah,
I
go
ask
ahead.
some questions? Okay.
Oh,
Thank you
sure,
very
sure.
much, Professor Kano. Very interesting talk. I'm Hendra, ex-colleague of
Mhm.
Agus, but a country fellow man. I'm Indonesian as well, but now I'm working in Korea in Gyeongsang National
Oh,
University,
okay.
the Department
Mhm.
of Aerospace and Software Engineering.
Oh, I
Well,
see.
you mentioned a lot of things that actually relevant to my current works. So, but before that, I would like to ask a few questions. Yeah, it's very interesting about the JIT, just in time approach.
Okay.
But you mentioned in one case you have the issue of data availability. Maybe I missed it. I think you explained
Mhm.
that. So how did you cope with this data availability issue? That's one thing. The second question is, among all your algorithms in this modeling or in estimation, and also saw in one of or several of your pictures about the connecting blocks between the plant, instrumentation, control, and processing the data, and it might involve optimization and so on and so forth. So how about the computational issue? Uh, because maybe if you are dealing with a real-time system, you might need a fast computation, and especially for the application of this epileptic seizure prediction, and it involves just a mobile phone. I don't know. Maybe there's a certain techniques to cope with the computational issue there, and I think my last questions. Currently, actually, my work, I'm working.
Oh, just a moment.
Uh,
Just a moment.
oh,
So
okay, okay,
I'm sorry. My network condition is bad.
oh,
So,
okay,
so let me answer one by one.
oh, okay, okay, okay then.
Okay. So, okay. The first question is that data availability, right?
Yeah, yes,
So, according to the just-in-time modeling, okay.
yes.
So your question is how to obtain enough data for using locally weighted PRS or other just-in-time modeling techniques?
It can be LWPLS or just-in-time
Okay.
approach in general.
So, okay. So, oh, okay. So let me show this example. Okay. So I explained about this.
Yeah, this example, impurity example, yes.
Yeah, application results. And in this case, okay, we have two towers. So we measured many temperatures, pressures, feed flow rates, and so on.
Mm-hmm.
And also, of course, we measured impurity content in the product. And the process variables, temperatures, pressures, and flow rates, and so on, were measured every second or so. However, the impurity content is measured only once a day. So that is the difference. Okay. But we have enough data in the past for about 3 or 4 years. So we have, in this case, we have sufficient data to develop locally weighted PRS or any other just-in-time models. So in this case, data availability is not the problem. And in many cases, in many industrial applications, yes, data is usually available, and we can build or we can use just-in-time models.
So in other words, if you have a database, then this approach is very effective. Can I say that?
Yes, yes, yes.
Okay.
But I think I need to say that, okay, so by using just-in-time modeling, this approach automatically rebuild local models. So actually, we do not have to perform model maintenance. However, we need to be very careful about database maintenance. If database include sufficient information or sufficient data, then just-in-time model successfully predict the output variables. However, the database does not have sufficient data or good data, then we fail to predict the output variable. So database management is quite important. Okay. Okay. So if you have a physical model or if you have a gray box model, then you don't have to adopt just-in-time approach because first principle model can cope with any operating conditions, right? So you don't have to use just-in-time approach. So we adopt just-in-time approach only when we try to use statistical model. It is not limited to locally weighted PRS, but yes, if we use statistical model, then just-in-time approach is very powerful to improve the prediction performance.
I think just now I also have the second question. Maybe.
Yes. Please go ahead.
Oh, okay. Maybe just now because of the internet connection. My question was about this one. So I saw that we need to process the data and it may involve optimization. And then, for example, in the application of this epileptic seizure prediction, and how do you manage this computational issue? I mean, because it just use, for example, a mobile phone, and then maybe it has a very limited computing power. So I think
Right.
they could also pose a challenge in order for that technology to be applicable for how to say public use, for example. Maybe you could share some of your
exactly.
Yeah.
Yes, it is very good question. Yeah, so we are tackling the computational issues. So actually, yes, the performance of smartphone is very limited. Okay, so our algorithm, our fault detection algorithm, is now customized to reduce the computational load as much as possible. So our algorithm is quite quite easily, our algorithm is easily implemented in the smartphone, even whose performance is very low, very limited. So, okay, so that is why we are using, for example, multivariate statistical process control. MSPC is a very simple algorithm for fault detection. So the computational effort is not a problem. However, okay, we might be able to improve the detection performance by using deep learning, but we cannot adopt that because computational effort is too much for us. To compute the model in the smartphone is very difficult. So the computational effort is a problem for us. Yes, you are right.
Thank you for your answers.
Prof. Prof, there's one question from the chat box.
Okay. Yeah, Professor Kano, there are two questions in the chat box. Perhaps I can start with the first questions here. So from Dr. Hasindra Sabiri from University Technology Petronas, her question is, what is the best way forward to deal with soft sensor development using a just-in-time model if the actual composition value of the output variable is only available twice per year? I believe it's the data limitation issues. Do you have any comment on that,
Yeah.
Professor Kano?
Yeah, of course, the measurement of output variable is really necessary for us. So the number of samples of output variables is too limited. Then we cannot apply any statistical techniques to that problems. As a result, yeah, I'm afraid that we cannot adopt just-in-time approach, not only just-in-time approach, but also any other statistical techniques. Yeah, so that is a problem. So in such a situation, only what we can do is to encourage practitioners or companies to measure the output variables more frequently. That's all, I guess.
Yeah. Okay. Thank you, Professor Kano. Dr. Hasinda, feel free to further ask the question if you have any. Let me move to the next questions. Inferential control might create a static offset, even though the model is highly accurate. Are there any acceptable tolerance for the offset or any other suitable method to remove this offset? Any comment, Professor Kano, to these questions?
So you mean the offset of the predicted values?
Yes. I think the question is from Dr. Saliwati. She mentioned that the inferential control may create a static offset, even though the model is accurate. So she is asking how to eliminate this offset and any acceptable tolerance that we may maybe set for the predictions.
Okay. Okay, so, okay. I see. All right. Okay, I see. Okay. So usually when using inferential control system, we assume that or we use the predicted values as measured values. So there is no difference between predicted values and measured values. So in other words, we believe that predicted values are equal to the measured values. So usually, if you are using a PID control system or model predictive control system, then static offset does not matter. So in order to remove or in order to cope with static offset, I think we should improve the control system itself, not the statistical model, but the control system.
Okay, thank you, Professor Kano. Dr. Saliawati, feel free to further comment if you have any. There is one more comment in the chat box. Let me try to read. I would like to ask about process system engineering application domain. If I'm good with the principles of process system engineering, can I apply them in the field of manufacturing? From Dr. Alawat. Do you have any comment on that, Professor Kano?
My answer is definitely yes, you can.
Yeah. Okay. Thanks, Professor Kano. Dr. Alawat, hope that is answer your inquiry. Otherwise, feel free to unmute yourself or make further inquiry.
So actually,
yes.
yeah, actually, my background is chemical engineering, in particular process systems engineering. And so far in the last maybe 20 years or so, we solved many problems in various fields, in different fields, by using PSC tools. So if you are good at PSC, the principles of PSC, then I believe you can solve many problems in other fields, including manufacturing.
Okay. There is one more question, Professor Kano, in chat box from Dr. Asindra Sabiri from University Technology Petronas. Have you ever deal with pseudo y, I think a pseudo output variable, to replace the lack of measured output variables? Do you have any comment on that, Professor Kano?
Oh, pseudo variables?
Yeah. Seems like maybe the main output variable is not available or difficult to measure or maybe infrequently measured. So I believe this Dr. Hasina asking whether this y can be replaced with maybe the secondary y, the secondary output variables. Dr. Hasindla, would you like to clarify? You can unmute yourself.
Hello. Can you
Yes,
hear
go
me?
ahead, Dr. Hasindla.
Okay,
Yes.
okay, thank you. I know that Prof said earlier that the only way forward is you must measure your output variables, right? But in some cases, probably due to cost-wise, it may not be possible. They can only have like twice a year using mobile phones, for example. So in this case, let's say you want to develop a sensor for that one, you have to be using some pseudo variable. I think you want to proceed pseudo output variable. That means something that can actually, because I'm looking at, for example, dynamic PLS, right? Dynamic PLS is a very good performance based on the literature. But for example, it requires the actual values of the output variable. For example, if it's for NOx measurement in your boilers or furnace, for example, for your NOx. So let's say you require the actual NOx measurement, but if you don't have that hardware sensor to measure that, but you still need to develop a model that can be adaptive to the environment, to the operating conditions. Have you ever dealt with some sort of like pseudo Y to represent the NOx behavior? That is my question. I'm not sure whether is that clear, Prof?
Oh, I'm sorry that network condition is too bad, but yes, partially I understand your question. And
thank you.
Okay, so if the measurements of output variables or important variables are not available, or the number of samples is strictly limited, then okay, the statistical approach is not useful. So we need to find another approach. And I think in such a situation, perhaps we may use a physical model. Once we can get a physical model or first principle model, then that model can calculate any variables, right? So even though the number of samples are limited or the measurement is not available sufficiently, we can build physical models. And by using physical model, we can predict such output variables. So yeah, I recommend to use physical models to solve such problems or in such a situation.
Okay, thank you so much, Prof.
Okay. So while waiting for other inquiry, Professor Kano, I have a few questions here. I noticed that in your LWPLS, your similarity factors are mainly based on the Euclidean distance and maybe Mahalanobis distance, with maybe some modification with the weightage. Do you think if we use other type of distance, we can further improve the model? I think we lost him. Okay. Let me try to raise him again. Hello, Professor Kano, can you hear us?
Oh, yes. Now
Yeah.
I can hear you well.
Okay. Yeah. I noticed in your LWPLS algorithm in the GIT framework, your similarity index is using Mahalanobis distance or maybe Euclidean distance, maybe with some modification by including the weightage. Do you think if we maybe use a different type of distance, we can further improve the model accuracy?
Yes. So yes, it is quite important to appropriately select the distance, definition of the distance. But unfortunately, before building a model, it is very difficult for us to know which distance is better than others. So yeah, unfortunately, we have no answer to that question. So usually when we apply locally weighted PRS or other techniques to real industrial plants, we choose the definition of distances by trial and error.
Yeah, I mean, because I'm wondering, because this Euclidean distance and Mahalanobis distance are very sensitive to outliers. So
Right.
did you carry out data cleaning first before the modeling, or
Sure.
Oh, okay. So
Sure.
basically, before you utilize the data, you carry out the maybe the outliers elimination first. Is that what you're saying?
Yes. So data cleaning or data cleansing is quite important. However, okay, so just-in-time approach, including locally weighted PRS, is more robust than traditional approaches to measurement noise or outliers, because in just-in-time approach, we focus only on nearest samples, right? And ignore samples located far from the query, right? And if one sample is outlier, then such a sample must be located far from the query sample. So such a sample, such outlier is automatically ignored in the just-in-time approach. So our approach, including locally weighted PLS, is more robust than the other approaches. However, when the query sample itself is outlier, then, okay, we can't do nothing. So data cleaning is quite important, or outlier detection and removal is quite important.
Okay. Yeah, I think it's well understood. My second question is related to your I believe you did some industrial survey in Japanese industries
Okay.
in 2009 or 2010. I think your paper was published in 2010 in the
Yes.
Journal of Process Control.
Yeah.
And I think congratulations that this is one of the most cited papers. Actually, we are very surprised on the finding on the artificial neural network, because in the scientific literature, ANN is a very popular, but seems like
Yes.
in the industrial application, it's
Yep.
not really a preferable choices. Do you have any comment on that? And do you think that in the future this trend may change?
So the results of this questionnaire survey clarifies that there was a big gap between industrial practice and academic research. So, okay. So in my feeling, many researchers are focusing on advanced technologies because to write as much papers as possible. Okay, so they are under pressures to write as many papers as possible. However, the situation in practice is totally different. Many papers are useless to solve the real problems. Okay, but as for neural networks, recently there are many good researchers are developing various neural networks models, and some of them are very powerful. And I think the number of applications of artificial neural networks, including deep learning, will be increasing in near future.
Okay. One last maybe inquiry from me, Professor Kano, because you have been, I think, exploring PCA, PLS, LWPLS for many years. And I think your group have proven that they are widely applicable, they are reliable and accurate, yet actually they are very simple compared to artificial neural net. Do you think that maybe in the next maybe 10 years or 20 years to come, this PLS and the variant are still competitive compared to the neural net, or I think the new trend now is a deep learning in the autoencoders?
Okay, my answer is yes. Yes. However, okay, so we have many problems, many target processes. So, okay, so we need to use appropriate tools for appropriate problems. So in some cases, PLS and PCA will be dominant in future. But in some other cases, we need to use deep learning to get to get good models. Okay, so yeah, which method should be used is depending on the programs.
Yeah, thank you, Professor Kano. I think it's a fair enough, and yeah, I think you are right in that sense. So thank you very much for responding to my inquiries. So for others, I think we still have possibly maybe maximum another 10 minutes. Any other opinion, comment, inquiry? Feel free to drop your message in the chat box. Otherwise, please unmute yourself.
Agus, can I have one more question?
Yes, please, Indra. Yeah.
Just curious, Prof. Kano. We are now living in the corona pandemic situation. So with your technique in this inferential technique would be helpful in any way. For example, in improving how we make a decision in coping with this pandemic, for example. Thank you.
Yes. So, okay. Today, I mentioned about our Okay, today I mentioned about our project to realize this epileptic seizure prediction. And now we are testing our system in hospitals. But to do so, okay, so university researchers actually cannot do that. So in order to commercialize our system, we have established our company named Quadritics company. And in that company, we have tackled many problems, including COVID-19. So what we want to do now is to predict whether the patient condition is rapidly getting bad or not from vital measurements. So in order to realize such system, we have to collect many data from real COVID-19 patients. So now we are collecting such data from several hospitals. And hopefully, maybe a half year or 1 year later, we can develop such a system to predict whether any patient getting worse, rapidly worse or not. So that is one project that I have.
Very interesting, Prof. Kano. Thank you.
Thank you very much.
Yeah, thank you, Dr. Hendra. Any other? Feel free to unmute yourself. Okay, so maybe I would like to maybe close this session with my question, Professor Kano. These adaptive inferential sensors, because it regularly update the parameters and some of the other internal factors. When we, let's say, implement this sensor in the control system, don't you think that the control stability at some point may be an issue? Because when, let's say, a control system try to maybe recommend an action, but the sensors itself is being updated. Do you have any comment on the stability of the control system?
Yeah. So not from the viewpoint of theory, but from the viewpoint of practicability, it is quite important. And okay, so when we adopt a statistical model, that statistical model cannot apply to okay, such successful model can interpolate, but cannot extrapolate, right? So it is important when we are using soft sensors or statistical models, the model can be used only in the region of interpolation. That model cannot be used in extrapolation region. So usually in practice, in the industry, when we are using soft sensors or statistical models, we have two models. One model is soft sensor itself, and the other model is to check whether the current condition is interpolation or not. In other words, the model is reliable or not. So if you do not have such support system or checking system, then the control system might be unstable. That's a very big problem.
Thank you, Professor Kano. I think that may wrap up our session today. So once again, thank you very much for the interesting and insightful talk. We are very privileged to have you today. So on behalf of the MyPCS, Malaysian Process Control Society, and everyone here, thank you very much. And hope that we can collaborate in the futures, and we can possibly have you again in the next webinar session.
Yeah.
Okay.
Yes. Thank you
Yeah.
very much.
So
yeah.
Yes.
Yes. Thank you very much for giving me this great opportunity at my PCS. And also, I really apologize, everyone, to attend this meeting due to my internet connection trouble. I'm very sorry about that. But I also hope that you enjoy my presentation. And yeah, I hope you try to solve social problems, important social problems by your technologies or by your researchers.
Yeah. Professor Kano, once again, thank you very much. We hope to have you
Thank you.
again in the near future.
Yes, I really hope so.
Yeah, and hopefully post-pandemic, we can have you in Malaysia. Yeah. Okay. Thank you, everyone. Take care and bye-bye for now. See you in the next webinar session.